the first one was number 12, and this will self-correct itself next week because we're going to talk about Riemann sums towards the end of the week. We haven't talked about them for a long time, so I get why this one was wrong. Here's what you need to do first of all. You are estimating the area under the curve of this function, and it's an estimate. You don't have your graphing calculator. You can't math 9 it. You are just going to go get an estimate, and it helps to get a graphical picture of what this looks like. This is an exponential function. They all look the same. So when you're trying to estimate the area under the curve, it helps to know what the curve looks like if you get stuck. If you're not stuck, don't do this. It would be a waste of time. But 9 to the x is an exponential function. It goes through 0, 1. It shoots up very steeply because of that 9, but just leave your axes delineated there. And then what you're doing is you're going to go from 0 to 2. I'm going to go draw that up to here, and you're going to estimate the area under the curve. You can't do it with geometry, although it's really close to a trapezoid. That curvature kind of blows that out. So you're going to chop it into rectangles. It says you're supposed to use 4 subintervals. So if you need 4 rectangles from 0 to 2, what does the base of every rectangle have to be? A half. So we're going to chop this, and I'm going to make the graph because it's been so long since we've done these, but really you don't want to spend time making the graphs. That's what that looks like. So what you're going to do is chop this into 4 rectangles that hit up on the right. So you're going to have a rectangle right here, and you're going to have a rectangle right there. You're going to have a rectangle right here, and then over like that. So you're going to do the area of those 4 rectangles, but it's easiest if you just make a chart for these. You're used to them giving you a chart. I'm going to make one here. So I've got x, I've got f of x. I'm going from 0 up to 2 by halves. So I'm going to go make a chart on this. By the way, how many of you had this one wrong? Yeah, that's what I thought. You'll see a ton of hands up because we haven't done one like it for a long time, but once I do, you'll go, oh, this is actually one of our easier topics. So the next thing I'm going to do here is go find how high I am. At 0, I was at 1. That's this dot right here. I'm going and finding these dots along the curve. And remember, I'm doing 9 to the x. 9 to the 1/2 would be 3. 9 to the first is 9. 9 to the 3/2 would be the square root of 9 cubed. And 9 squared is 81. And again, that represents this dot right here is 281. It says to do right rectangular approximation. So which dot don't I use? Yeah, the leftmost one over here. And you can see it, I missed it. All these are the heights I want to use for my rectangles. I'm sticking to the right. Again, if it had said a left Riemann sum, then we wouldn't have used the 80 and everything would have hit over on the left. So really I need to do the base of every rectangle, and for this one it's consistent. So I do 1/2, because that's the base of each rectangle, and then for this one I do 1/2 times 3. And then I do 1/2 times 9 plus 1/2. I'm going to pull the 1/2 out front. So I do 1/2 of 3 plus 9 plus 27 plus 80. All right, so just base times height gives me 4 rectangles. They all hit over on the right. This, if you add it up carefully, is 120. Don't circle that. Anyone circle 120? That's the mistake you don't want to make, because that means you know exactly how to do it. You go through all the math, and then you forget that you pulled a half out front. And you're going to find a lot of those when you correct yours. And that we're going to try to, at this point, I'm not going to be teaching you a whole lot new. We're going to avoid making little mistakes. That one's done. It would be 60. Yes. Oh, that should have been an 81. Sorry. That's me having a brain fart. I wrote 81 over on the graph. All right, next one up. Number 20. This was a little rule that we had, but remember, whenever you're approaching a constant, you plug it in when you're doing a limit, and you hope you don't get what I'm going to get on this one, because I'm going to get ln 5 minus ln 5 over 2 minus 2. Unfortunately, I get 0 over 0. That doesn't mean go circle E. It means you need to have another plan of attack. Usually your plan is to factor, cancel, find where the hole is, but that doesn't work on this one. But we did have a guy, L'Hopital. Yeah, this is L'Hopital's rule. You can use it for this indeterminate form or for this indeterminate form. And what L'Hopital's rule says is you can do the exact same limit of the derivatives of the top and the bottom. So the derivative of ln of a function is 1 over it times its derivative, which is still 1. This is a constant, so that'd be 0. On the bottom, the derivative is 1 minus a constant. So now when I replug after using L'Hopital's rule, the answer falls out nicely. That's an easy one to fix. If you got that one wrong, that's an easy one. An easy one to fix, not an easy one to do. Number 23, how many of you put C? Just out of curiosity. I would have too, honestly. I almost did when I made the key and I stopped I actually had put C and then I was like, oh wait, I better make sure, and it wasn't C. So kind of a trick question in a way, but let's go take a look. First of all, in order for me to be able to take a derivative, what does the function have to be? Continuous. So the first thing I would do is check for continuity. That arrives up at 2 when you plug that in. This arrives up at 2. So I know that there's no gap and that they're meeting nicely. So then I think what your gut instinct is to say, all right, this falls on this piece. I need the derivative there, which is negative 2x at negative 1, which would be 2. And then you go and circle C. But I just told you that's wrong. Here's why. What else has to happen for it to be differentiable? Because continuity is great, but I also have to make sure, yeah, that the slopes or the derivatives are the same from both sides. This one's got a slope of 2, right? At negative 1, what's the slope of this? 3. What that means is I've got an upside down parabola meeting an uphill line and it's not smoothing out. It's an indicator that there's a cusp there. So kind of a tricky question. When I made the key, I circled C and I was like, oh, I forgot to make sure. And then I was like, oh, they really did do that. Like they made it. How many of you caught that? That's a good catch. It's one of those details. It's one of the reasons why one person in the entire world usually aces the AB exam. It's little stuff like that that most people miss. Number 24, once I put it in better language, again, we'll straighten it out. So I'm kind of glad we didn't get any big concepts. These are little details. The detail on this is you really have to understand that a horizontal asymptote of any function, I'm going to make a fakie here, and I'm going to go like that, and suppose this is up at 2. This horizontal asymptote is the line y equals 2, correct? Really what it is, though, is it's the limit as x approaches what? Infinity. Yeah, horizontal asymptotes are limits as you approach infinity, or negative infinity. I could actually have one down here too, another horizontal asymptote, but they're limits as you approach infinity. So once you know that, which I just told you, so you won't do it again, you're really just taking a limit as x approaches the infinities for this, and that we know how to do. For polynomial functions, we analyze the highest powers. What's the highest power on the top? Second degree, and the coefficient, it'd be negative 12x squared. That's controlling the end behavior, plus other stuff, but I don't care about the other stuff. Same on the bottom. If I were to FOIL that out, I'd have 4x squared plus other stuff, but I don't care about the other stuff. It's these two who are controlling the behavior. So as I go to infinity, what's my limit? Negative 3. And as I go to negative infinity, it's also negative 3. Be careful with that, though. I'm going to go circle this, but I'm going to put out a little warning because it happens on a practice test, either yet to come or I remember making a key for, suppose it had been this instead. So suppose the highest degrees had been to the 3rd degree and you were looking for your horizontal asymptote or totes. When you do a positive infinity, what's the answer? They have 3. But when you do a negative infinity, it's still negative 3. Let's change that. Will that change it? Still. No. That's still. I don't know. There's one coming up where when you approach one of the infinities, it's a positive, and when you approach another one, it's a negative. So just make sure you kind of approach both infinities. And again, code language for horizontal asymptote is a limit as you approach the infinities. That'll clear that up. This one can be done with common sense or with calculus. So we're going to take common sense like a physics approach. This is really your number 29. All right. First of all, you're looking for average velocity. If you're in physics class, how do they tell you how to get velocity? Because you only do average because instantaneous is a derivative. How do you get average velocity in physics? You have a formula for it. Delta x over delta t. That's the physics formula. And in physics, you do, in non-calc based physics, you just do change in position over change in time gives you your average speed. You can even think of that when you're driving. You know what I mean? How far did you go? Over how long did it take you? That's your average speed. If you take the calculus out of it, which one of these is showing change in position over change in time on that interval? A isn't. C is. Yeah, this would be where were you at 8? Where did you start at 2? That's your change in position over how long did it take you. That's a non-calculus approach, which is totally legal. Here's the calculus approach to it, though, because some of you will like that better. When we are doing average velocity, maybe you want to consider it as average value of the velocity function, because average value we know how to do with calculus. We do 1 over what? Average value of a function. B minus A, so there, times the integral from A to B of the function you're finding the average of, which in this case is the velocity. And you'll notice you don't see that up here, but here's why. What is the antiderivative of velocity? Position, yeah. So this is really 1/6 of the position function evaluated from 2 to 8. And that'd be S of 8 minus S of 2 over 6. Does that make sense? So either one is good. A lot of times they'll ask you what's the average acceleration. That's a common one too. Well, it's the average value of the acceleration function, maybe from 2 to 8. Don't write this down like that. But what can you use as your antiderivative for that? V, yeah, V of 8 minus V of 2. So you can use the calculus or you can just use common sense on that one. How many of you on number 78 put E? Own it, because you're getting my favorite wrong answers, Olivia. That means, nope. Yeah, E on this one is the best wrong answer. The other ones don't make sense right from the get-go because this is the graph of f prime is what you're trying to do. The y values are representing f prime, and it says that f is increasing. So if f is increasing, f prime, which is y, has to be positive. So you can't pick any graph that dips below the x-axis. So B is out, C is out, and D is out right from the fact that f has to be increasing, because then its derivative has to be greater than 0, and this is the graph of the derivative, so I have to be above the x-axis. But to narrow it down between the other two, f also has 1 point of inflection. What that means is f double prime can change signs only once, right? Or f double prime equals 0 and changes sign twice right here, right? F double prime is positive because f prime is increasing, then it's negative, then it's positive. I have an issue there. So the answer would be letter A, where f double prime changes sign once at that cusp. All right, here we go. Last one that I'm going to do with you, and then you're on your own. They usually do give you a screenshot of some tables and ask you to kind of analyze using information that's a couple steps beyond. Number 80 for you guys, can you tell me what number that is? It's year 33. This is the last of the most missed. Here's how you got to approach one of these. First of all, they give me info about f double prime, and I somehow have to work myself back so that I can only use f. So I'm going to go back one tier. If f double prime is greater than 0, what do I know about f prime? It's increasing, okay? So f prime, the slopes of the tangent line, has to be increasing. Well, they didn't give me f primes, but they gave me screenshots. So I can find the slopes here and the slopes here, and I know whatever happens at 3 has to be between them because it's increasing. Does that make sense? So what I'm going to do is go find the slope. This is just algebra 9, change in y over change in x. I'm going to go get a slope here, and that would be 3.6 minus 2.4 over 2. So 1.2 over 2. Or 0.6 is the slope directly to the left, okay? Then directly to the right, because it says at 3, so I'm going to go over here and take 3 to the next one. I'm going to subtract these, and I'm going to get 1.8 when I do 5.4 minus 3.6 over 2, which is 0.9. So now I know what's happening right directly in front of it and right directly after it, and I know it has to be increasing. So who's my only option? Yeah, 0.7. So out, 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 out. Here's the answer. So your task is to take that orange sheet, and on it you are going to show the work to fix all the other ones you got wrong. Some of you, that'll be about 5 minutes, some more. But if you don't know how to fix it, I did post a key in Schoology, like a worked out solution key. So you can give it to me by the end of the hour if you want, or you can wait, I don't care.